Hey guys, I am already selected for a jury, so I'm going to try and record my lectures so that you guys don't fall behind. So, coming at you from the courthouse. You want to say hi to teenagers?
Hi guys.
That's some of my fellow jurors. We're making friends. So, here we go. Okay, so today's lecture is going to focus on ray diagrams for lenses. Okay, so ray diagrams were those pictures we use to sort of figure out where an image would be for mirrors. We can also do those for lenses. There are some differences. Okay, first of all, when we were talking about mirrors, we were using the law of reflection. In other words, if we had in a mirror, if we had laser light coming in flat like this, we would go zoom in on the surface. I don't know if it lets me zoom in anymore. And you could look at, okay, if it's hitting, and this is not obviously a flat line, if it's hitting this surface at an angle of like 30 degrees from the normal line, then it has to be reflected at an angle of, ooh, wow, that's really bad. It has to be reflected at an angle of 30 degrees to the normal line. Okay, that is a terrible representation because I did not draw this picture very well, but you get the idea. So that is the law of reflection, and that is why the laser light kind of came to a focal point. What we're going to deal now with is with lenses, the law of not the law. We're going to deal with refraction. In other words, Snell's law, which is, how light bends. And we learned that in level, I think, 3 of Optics 1. Okay, here's what's happening with lenses. So here's an example of a lens. And this is a converging lens. How do I know that? Because it is thicker in the middle than it is at the edges, okay? A diverging lens will look exactly the opposite. It'll be thinner in the middle and it will be thicker at the edges. So in a converging lens, let's follow the path of light. So here comes in like a laser, a white light, and it hits here, okay? What happens then? Well, you can see a little bit in the picture. It's not great, but you can see it a little bit. What happens is the light, which was moving along at a steady pace, pretty close to the speed of light, is now going to hit this material and slow down. So we use Snell's law. The reason lenses work is because they have this curved surface. So if you can imagine, there's your tangent line. If we zoomed really far in, here would be your 90 degrees to the tangent line. Oh gosh, that's terrible. I have to redraw that. Oh my gosh, teachers make mistakes too. They probably make more than you. Okay, so that's pretty 90-ish. Okay, so in this situation, this is my angle of incidence. And what's going to happen is when the material comes in, you're in a material that's less dense out here. So when it comes in here, it's going to be bent. Okay, and that's what refraction basically means. So the angle that refraction is going to be smaller, and I'm exaggerating it here so you can see it, than the angle of incidence. So angle of incidence will be bigger than the angle of refraction because we're entering a more dense, higher index of refraction. So out here where there's a small index of refraction, there's a much larger index of refraction. I know my picture is not particularly good. I'm kind of sketching them without anything, but you can see the light is going to get bent there. And that's basically what's the lens is going to do. It's going to bend it here, and then it's going to bend it again when it comes back out. Okay, so, light comes in, gets bent again, and it's converging all to this focal point. So when we're going to be drawing ray diagrams, notice that you can almost kind of see the image here, flat to focal is happening. We're going to be using that, we're going to kind of be exploiting it. Also notice that if you go straight through, the light just keeps going. In fact, we're going to use that as well, that idea as well when we do these ray diagrams. There's one other small difference between doing a ray diagram for a mirror and doing a ray diagram for a lens. And that's actually where the observer would be. In other words, where is the person that's physically seeing this image? So when you did the whole mirror thing, you would sometimes get, let's say this was your original object, you would sometimes get images that were like this. And that meant that if a person was looking here, they would have to put a screen here in order to see the object because it's in front of the mirror. That's a real image. If you had an image appear behind the mirror for whatever reason, and it would be bigger. I'm running out of space here. It's bigger. Okay. In that situation, it would be as though this person here, this little eyeball here, oh gosh, they've gone anime. Okay, they would see the image from this perspective looking at the mirror. So it would look like the object was inside of the mirror. When we are doing lenses are a little bit different. We're going to be doing ray diagrams in a second, and you might have your object here, and you're going to find that maybe your image shows up over here. Now when you do lenses, you imagine that the observer is over here now. It's on the other side of the lens, okay? Wow, that's a giant eye. That person needs to get it looked at. Wow, I'm just gonna put a hat on them. Maybe they'll feel better. Oh, it's starting to look like the Pope. I'm sorry. Okay, hold on. We gotta go back. Okay, I regret my hat decision. So now if you put the observer over here, that means this is a real image over here. So you'd have to physically put a screen here in order to see it because real images are on the same side as the observer. If you were for, a different kind of lens or a different scenario with the lens, find that the object was over here, okay? Or I'm sorry, the image was over here. So this is your object. This would be your image. Then the observer is on the opposite side of the lens. So now this would be virtual. It's like you're looking through the lens and you're seeing the image on the other side of the lens.